Well, hello, my good friends. Today I want to talk about properties of logarithms. So if you'll get yourself a pencil and paper so that as you're thinking, you can be writing, and then as you're writing, you can be thinking, because those two things go best when they go together. But let's review briefly some properties just of exponents. These are simple things we've done before. So if I had, say, like a base raised to the m exponent, and I multiply it by the same base raised to the n exponents, you know that I keep the base and then I add the exponents together. So what was a product becomes a sum. I was multiplying the bases and then I can switch and add the exponent. And that is the product property of exponents. Now there's a quotient property too. If I have b to the m divided by b to the n, the same base, then what I do is I take the base and I subtract m minus n. So what was a division problem becomes a subtraction problem. And there's one more, there's the power property. If I have b to the m raised to the n, I can keep the base and then multiply m times n. Multiply the exponents. And since a logarithm is a rearranging of the exponents, right? Remember, a logarithm asks what is the exponent on the base that gives you the power. We have similar properties here. So the product property of logarithms, the product property says this: if I have a logarithm, base b there, of m times n, these are two things that are multiplied, I can then make them a sum. I'm going to add something together. Something that was multiplied becomes something that is then added. What is this something that's added? It's two different logarithms. It's log base b of m plus log base b of n. So I had a product of the arguments there, a product of the powers, and I can make it a sum of two different logarithms. And let's just jump on ahead here and I'll show you this example. So the question number one says, rewrite the logarithm as a sum difference or multiple of log base 10 of 5 and or log base 10 of 7. So the first question here, log base 10 of 35, and I'll put parentheses around my power because that's really a good idea. How do I get 35 from something, 5, and 7? Well, hopefully you can see very quickly that this is log of 7 multiplied by 5, and you're going to say, you didn't write the base. You're correct, I didn't, because it's base 10, and when there's no base written, it's understood to be base 10. So now I have a product of 7 and 5. I can make that a sum of log of 7 plus log of 5. You say, why would you be interested in this at all? Well, which is an easier operation to do, especially by hand without a calculator? Is it easier to multiply two things together, or is it easier to add two things together? I would propose to you that multiplication is more complicated than addition because it's repeated addition of the same thing. And so it's actually a simpler operation to add than it is to multiply. So if you're using logs, you can take something that's multiplied and you can make it something else that's added. That's a benefit. Let's go over these next two then. Quotient property of logarithms. So again, here I've got the power is being divided, right? So it's m divided by n. So I can make that a subtraction problem. It is going to be log base b of m minus log base b of n. So what was a division problem now becomes a subtraction problem. And again, let me ask you, which is easier to do without a calculator, to subtract or to divide? I would say it's easier to subtract. And this is the one really that gives you the power. Log base b of m raised to the n, okay, that's going to be this. I can take this exponent here of n and I can move it out in front as a multiplier. So this becomes n times log base b of m. Now, this is the one that really got the most traction historically. Maybe you've heard of the astronomer Johannes Kepler. He was the astronomer that said that the planets orbit the sun in ellipses. That was one of his planetary rules and so forth. He came after Copernicus. Copernicus said they went in circles. Kepler did the math and showed that they actually went in ellipses. But one of Kepler's laws involves a fractional exponent. And he credits a man by the name of Johannes Napier, who developed the logarithms, with his ability to make that mathematical insight. Because instead of raising something to a fractional exponent, one of his planetary laws is something to the effect of that the time it takes the planet to go around the sun is proportional to the radius of that planet to the 3/2 power. And so which would you rather do by hand? Raising something to the 2/3 power, which is a square and a cube root simultaneously, or would you just rather multiply it by 2/3? So Johannes Kepler said that Napier, through the logarithms, effectively doubled the life of the astronomer. Not because he lived twice as long, he's just able to get twice as much work done because he's multiplying now instead of fractionally exponentiating. So it's a little historical background for you there. So what we can do then is we can take an exponent and we can turn it into a multiplier. So let's see now how this works here on number 2. So log base 10 of 25. Gee, how do I write the power here as something 7 or 5 or some combination of them? Well, this becomes log of 5 squared. And so I can take the exponent of 2 now and I can throw it down as a multiplier. This now becomes 2 times log of 5. Okay, and again over here on this one, number 3, log base 10 of 7/5. There's your argument. Okay, so this is now going to be log base 10 of 7 minus log base 10 of 5. So that's how you would write that in terms of simpler things. Okay. Now, the next type of questions does the same thing, but this goes and says, okay, so use log base 10 is approximately this decimal, and log base 10 is approximately that decimal to approximate the value of each expression. This again goes back to how you would do such a thing without a calculator. You used to have log tables, and you have to look it up in a table. But I'll give you an example of that. Let's do number 6 here. Log base 10 of 175. I've got to figure out how to do 175 as something involving a 7, a 5, or you can use the base. I could use 10 as a number, or you can use maybe 1. Those are the convenient things to use. And if you give it some thought, you will perhaps see that this is equal to log of 5 squared times 7. Right? 25 times 7 is 175. Okay, let's split it up now. Let's break it down. We've got several different things. I have both an exponent and a multiply, but the exponent only applies to the 5. So I have to separate the 5 from the 7 before I can do the exponent. So this becomes now log of 5 squared, plus or minus? It's plus. Log of 7. And now I can bring the exponent down as a multiplier. This now becomes 2 times log of 5 plus log of 7. And now I replace log of 5 and log of 7 with their decimal approximations from the instructions up above. So this now becomes 2 times, what is it? What's log of 5? 0.6990. And plus then, what's log of 7? Approximately 0.8451. And then when you do that very simple math, you're multiplying by 2 and you're adding 4 decimal places, I get 2.1831. Okay, so there's my final answer. Okay, now we can also use this to solve equations. Solve equations and check your solutions. We'll talk about that in a second. Here's my power there, there's the 1 power there. I notice I've got this multiplier. This is 2/3 times that. So I'm going to put the 2/3 up on 8 as an exponent. I could go backwards with the power property. So this is now going to be log base 7 of n, and notice since my base is not 10, I have to write it. Log base 7 of n is equal to log base 7 of 8 to the 2/3. And now, as we saw previously, if I have log of one thing and log of another thing, both with the same base, are the bases the same? Yes. So stop. New equation. I can say their arguments have to be equal. N then is equal to 8 to the 2/3. And what's 8 to the 2/3? We'll do the cube root of 8, that's 2, and then square it afterwards. I get n is equal to 4. Okay. Now, checking my solutions. Does n is equal to 4, when I put it back up into the original, does it make any of the logarithm arguments negative? Because you cannot take the logarithm of a negative number, or 0. And it doesn't, so that one's good. Okay. How about this one? All right, so I see 3 different logs here. Here's my equal sign, and I've got 2 of them on this side, but I see that they're being added, and they're both base 6. So if I'm adding logarithms, I can combine them into a single logarithm. Log base 6 of, what do I do with the arguments here? I multiply them together. Log base 6 of 9x. That's equal to log base 6 of 54. Okay, if it's log base 6 of 2 different things, then these 2 different things must therefore be equal to each other. Are the bases the same? Yes. Stop. New equation. 9x is equal to 54, and then just divide by 9. Divide by 9. X is equal to 6. There we go. Okay, check it. Does it make any one of the arguments negative? Nope. So we're good. Ready? Oh boy, this one's a little more involved. All right, so here's my equal sign. I've got 2 different logarithms and they're being subtracted. Let me put parentheses around the argument there and around the argument there so you can keep it straight. All right, so let me combine the logarithms on the left. It's going to be a single logarithm, log base 9 of, now what do I do with the arguments when I subtract the logarithms? I divide them. 3u plus 14 divided by 5, and that's equal to log base 9 of 2u. And now we're back to the same spot we were with all the previous ones. I've got log base 9 of something on the left and log base 9 of something else on the right. Those 2 things must be equal to each other. So 3u plus 14 over 5 is equal to 2u. And now I just solve it using some basic algebra. Multiply both sides by 5 to clear that. Times 5 here. This becomes 3u plus 14 is equal to 10u. I'll subtract 3u from both sides. Minus 3u cancels, and I get 14 is equal to 7u. Divide by 7, cancels. U is equal to 2. U equal 2. Do you? Now, if I put that back into the original, does it make any one of the arguments negative? Well, 3 times 2 is 6 plus 14, that's a positive number. And then over here, 2 times 2 is 4, that's a positive number. So this one still works, okay? All good? You can break the logs apart into smaller pieces, and then you can use the same properties to put them back together into a single logarithm. Okay, so let's try the next page. I'm going to do this equation here. All right, this one's a little more involved. So I've got, again, here's my equal sign that separates my sides. I've got 2 logs that are being added to each other. They both have the same base, so let me combine their arguments. Log of, what do I do with the 3m minus 5 and the m? I got to multiply them. So it's going to be m, I'll write that out in front, times 3m minus 5. In fact, I'll tell you what, I'll use a different shape grouping symbol so that you can see the group. There's the one group, is equal to, there's the argument there, log of 2. So I'm combining my arguments into one. Now, 2 logarithm on the left, logarithm on the right, the bases are the same. Stop. New equation. M times 3m minus 5 has to be equal to 2. Okay, now this is just quadratic. Multiply the m through. 3m minus 5m, and then subtract 2 from both sides. So minus 2 is equal to 0. Okay, this is quadratic. Oops. M squared. Because it's quadratic. All right, so you can use now the quadratic formula, or you can use the factor method. It does factor. The quadratic formula would always work. Some middle work here that you're going to need to do on your own. When I factored it, I got 3m plus 1 times m minus 2 equal to 0. If two or more factors are multiplied and the product is 0, one or more of the factors must be equal to 0. Again, stop. New situation. 3m plus 1 is equal to 0. So if I subtract 1 divided by 3, m is equal to negative 1/3. And then I get m minus 2 is equal to 0, so m is equal to 2. But I've got to check them both. If I put negative 1/3 up in here, it's going to give me a positive. That'll be a positive here in the first argument. Oh, but look right there. That argument there is just m. I wind up doing log base 10 of negative 1/3, and I cannot take the log of a negative number. So this is an extraneous solution. Okay, what about this one? What about 2? If I put 2 into the first one, it becomes 3 times 2, which is 6. 6 minus 5 is still positive. That's okay. That one's all right, and then that one's just a constant. So yeah, my final answer then is just m is equal to 2. That's why you have to check your answers. Now, number 23 here. I think we'll stop with this one. This one's a little bit different. There's my equal sign. I've got two logs that are being added, so the bases are the same. I'll combine their arguments. Log of 4 times w is equal to what? 2. Not log of 2. So what do? Well, what does logarithm ask? What's the exponent? So what's the exponent on 10 that gives me 4w? Well, the answer, the exponent is 2. So just do the log loop. Just rewrite this now as an exponent. 10 to the second is equal to 4w. Waha! 100 is equal to 4w. Divide by 4, divide by 4, w 25. Does it make any of the arguments negative? Nope. There you go. So in the previous questions, we had equating the arguments of the logs, if you had log on the left and log on the right. This one's not equating the arguments. This one is just simply rewriting it as a logarithm when you only have a single one. Just convert it into exponent form and then solve it. Okay? Well, I hope you learned something, and I hope you have a great day. Bye-bye.